So today we're talking about properties of parallelograms, and we know that quadrilaterals are just four-sided polygons. We're going to talk about specifically parallelograms today. So in your notes, we have these 6 properties of parallelograms that we want to be comfortable and familiar with. And most of it's based on the symbolism that you're going to be given. So if you notice that you see arrows, then you know, of course, that those mean that those sides are going to be parallel. So we define a parallelogram as a quadrilateral with both pairs of opposite sides that are parallel. Second, we see that we have tick marks, and we know that tick marks mean that we have sides that are in equal lengths, so both pairs of opposite sides are congruent, is our second property of parallelograms. When we notice that we have angles that are congruent, then we're going to say that both pairs of opposite angles are congruent. All based on the symbolism that we've used before. Our next one, hopefully we noticed when we were investigating polygons, or investigating parallelograms specifically, is that the consecutive interior angles have a special property. So we have to know what it means to be consecutive and interior. Interior means inside the parallelogram, and consecutive means next to. They share a side. So consecutive interior angles would be something like this angle X with this angle Y. They're next to each other, they share a common side. They're not opposite each other. X and X are opposite each other, whereas X and Y are next to each other. And we noticed during our exploration yesterday that X plus Y had to add up to 180 degrees, so we say that they are supplementary. The next property that we discovered was that when we have 2 diagonals of a rhombus, or a parallelogram, this diagonal of this parallelogram intersects the other diagonal that connect the opposite vertices, and they actually form 2 segments that are congruent and 2 other segments that are congruent. So it cuts the segments in half. That means that the diagonals are meeting at the midpoint, or the diagonals bisect each other. And our final property, we didn't get to discover this one, but it turns out that if you have a quadrilateral and you can make one pair of opposite sides not just congruent, but also parallel to the other, we end up with a parallelogram. So if one pair of opposite sides is both parallel and congruent, that forces that quadrilateral to be a parallelogram. So these are 6 properties that we have to know and have to be able to use to justify our responses to things. So let's see how much we remember. If we're completing this statement about parallelogram ABCD, segment BC is parallel to which segment? So BC is this one. We have parallel marks that match the parallel marks on segment AD, so the opposite sides of a parallelogram are parallel. Definition of a parallelogram. Our second statement says that segment AB is congruent to some other segment, so A to B would be the same length as D to C would, or CD, depending on which way you want to write it. They're the same segment. Our third statement says angle ADC. We have to use a 3-letter combo here because we have 3 angles here at angle D. So ADC is going to be congruent to which angle? The one that's opposite it. So angle ABC. And finally, EC, the distance between E and C, is equal to, this distance is equal to 1/2 of what distance? So that is half of this whole diagonal AC. So the distance between E and C is 1/2 the distance between A and C. So for the following parallelogram, we're going to find the values of W, X, Y, and Z, and V. So we can start anywhere. V seems like a logical place to start. V is a segment that is opposite the 16, so V has to be 16. W is a segment that is opposite 13, so W has to be 13. X is an exterior angle to this parallelogram. When we have two parallel lines cut by a transversal, our corresponding angles are congruent, so X has to be the same as 118 degrees. Y is a linear pair with X, so if X is 118 degrees and Y and 118 have to be supplementary, we subtract 118 from 180. 118 minus 120 would be 60. We're 2 more than that, so 62 degrees. And finally, we need to find angle Z. Angle Z is opposite the 118 degrees. Because opposite angles are congruent, Z has to be 118 degrees. In our next example, we're asked to find the values of X and Y. So when we look for X, we notice that 2x degrees is opposite the 54 degrees, so 2x has to be equal to 54 degrees. Since opposite angles of a parallelogram are congruent, we divide by 2, and X is 27 degrees. 3y minus 4 represents a segment that is opposite the 20, and so it's going to be equal to 20 because opposite sides of a parallelogram are congruent. Add 4, and 3y is equal to 24. Divide by 3, and y is 8. The next question asks, how can you verify that PQRS is a parallelogram, aside from my obvious parallel marks that I forgot to take out? So we know that opposite sides are parallel based on the definition of a parallelogram. And we know that parallel lines have the same slope. So one method that we could use to show that this is a parallelogram is we could find the slope of our 4 sides. Slope is rise over run. It is the change in y over the change in x. When something like this is graphed, it's very easy to see that from P to Q, I am rising 2, and I am running 4. So for the slope of PQ, I will have 2 over 4, rising 2, running 4, which reduces to 1/2. Let's verify that RS has the same slope. So the slope of RS, we fell 2, and we ran 4 to the left, so our slope is -2 over -4. A negative over a negative is a positive, so this reduces to a positive 1/2. They have the same slope. Let's check out the slope of PS, excuse me. So from P to S, we are falling 2 and running 4. So it has a slope of a negative 2/4, or negative 1/2. And the slope of QR, we went up 2 from R to Q and left 4. So we have a negative 2 over negative 4, and that reduces to a negative 1/2. These two have the same slope. Therefore, we have a parallelogram because both pairs of opposite sides are parallel. All right, next. We want to find the coordinates of the intersection of the diagonals of parallelogram LMNO with vertices L at 1, 4, M at 7, 4, and N at the order pair 6, 0, and O is at the order pair 0, 0. So if we graph these 4 points, we're trying to find the coordinates of the intersections of the diagonals. Diagonals go from vertex to its opposite vertex, vertex to its opposite vertex. So we can have a rough idea that we think it might be 3.5 over and 2 up, but we want to verify that algebraically or using our midpoint formula. So we think that these two are intersecting at their midpoint, and we believe the midpoint is 3.5 over and 2 up. So let's actually use the midpoint formula. The midpoint is found by adding our x's and dividing by 2, and adding our y's and dividing by 2. So if we add 1 to 6 to find the midpoint of LN and divide that by 2, and we take the 4 plus 0 and divide that by 2, the midpoint of LN is 7/2, which is 3.5, and 4/2, which is 2. So we were spot on thinking that that was 3/2, 3.5, and 2. But let's verify that OM also has that same midpoint. So from O to M, we're taking 0 plus 7 and dividing by 2, and 0 plus 4 and dividing by 2. And once again, we get 3.5, 2. 3 vertices of a parallelogram are listed. We're supposed to find the coordinates of vertex y. These are easier to do if we have graphed the 3 coordinates and connected them. And so we have a parallelogram. We know that our 4th vertex will be somewhere in this general area in order to make a parallelogram. We also know that opposite sides of a parallelogram have to be parallel. So we can check out the slope of segment WZ. WZ is falling 1 and going to the right 5. So from X, if we fall 1 and go to the right 5, we believe that our point could be right here, point Y. Let's verify by finding our other midpoint, or other slope. So from X to W, we went down 1, 2, 3, 4, 5, and over 2. So that means from Z, we would need to go up 5 and left 2, and that does put us at the point 2, 1. And now we know that we have our parallelogram.